This third chapter that I commonly teach the kids as forces and moment. We talk about equilibrium, conditions for equilibrium, how can it be equilibrium achieved, how can we work with vector diagrams, or more specifically, vector triangle, vector triangle rule, parallelogram rule, and also we have a new addition, a new addition in, with our O levels knowledge that is called polynomial rule. So we're gonna see about those as well, and then uh, we also additionally we have the idea of how to divide forces into components. So with angles, how can we divide the forces into components? I'm going to show you that as well. And we have Lami's theorem for the three forces to be in equilibrium. We can Lami's theorem is not necessarily a part of the syllabus, but it is accepted as a useful or allowed resource that you can use in applicable cases. So we're going to see about that as well. So, and obviously Newton's third law, the three laws of Newton, Isaac Newton, they are essentially with us. So this pretty much covers the first chapter. And then we have moment. Moment is, I mean, you would have to essentially remember everything that you've learned in your O levels for the moment or turning effect of forces chapter. Still, I'm gonna give you a quick I'm gonna give you some revision on what you are supposed to remember so that you can grasp the idea easily. Additional to that, we have to understand the idea of what do we mean by a couple or moment of a couple, where we have a pair of forces working in a specific mechanism. And then we also have to see that what are the conditions for an object to roll over, or what are the conditions for an object to start sliding. So how can we how can we affect the stability, or how to analyze the stability of an object? We're going to see some mathematical working for that aspect as well. So let's go ahead and try and see what are the things that we can cover. This is the class note from Parisa where we have these ideas. So the first thing that is covered over here is that we can have an object to be uh, to, to be in equilibrium by supporting it by, I mean, here we have two figures. I think I explained something over here, but I do not know what did I try to explain. What is it that I did try to explain? আচ্ছা, এই জিনিস আপাতত মনে নাই। I'll remember this definitely. Somewhere in my lecture it will pop up, and then I'll come back to this figure if required. So let's have a look at this further on. The one of the important thing that is given over here, that conditions of equilibrium. Uh, this thing for if any object has to be defined to be in equilibrium, we have to fulfill two set of logics. The first set of logic is that resultant force equals to 0. So this is the resultant force, which is supposed to be 0. This much is good enough, or you can write resultant force is 0, or you can further elaborate this if you feel that the resultant of the horizontal forces is also 0, and the resultant and the resultant of the vertical forces is also 0. So this kid over here has written that resultant fx plus resultant fy equals to 0. That also perfectly makes sense, because resultant fx would be the sum of all the horizontal component of all the forces, and resultant of all the vertical components, that also has to be fy means the sum of all the vertical component of the forces. Now, what do I mean by component? I'm coming to this idea just in a moment. I'll show you this over here. And if you do a vector sum of these two amount together, they should give you 0 if an object is supposed to be in equilibrium. This is the first logic. So there are two logic for equilibrium. First logic is that resultant force has to be 0. The second logic is that resultant moment of the object has to be 0 as well. Resultant moment of the object has to be 0 as well. So resultant moment should be 0, which means anti-clockwise moment equals to clockwise moment. So we have to maintain this as well. So if an object has zero moment, then we can also apply multiple other logic to this as well, which you're gonna see in a bit. Okay. Uh, what is shown over here is how can we divide the forces in appropriate components for our purpose. For example, the figure that we can see, I might as well copy this and take it up. Okay, I believe in this case, I was trying to explain the case how to find out the moment of an object in two different easy ways. I'll explain this to you in a bit. But before that, I would like to talk about how can you work with components. What do we mean by components in the first place? Now, if you remember Pythagorean rule, if we have a right angle triangle, in that case, it's very easy to work with these three components in basic logic. The basic, I might as well draw this triangle a bit. I try to draw an obtuse triangle where the three sides are not equal to each other in any pair. So let's say we have an angle of theta over here, and this is a right angle triangle. So this is theta, and this is our 90-degree angle. And then I can very well write that this is my adjacent side, and this is my opposite side, and this is my hypotenuse. This is the preferable notation that I prefer to use, other than base and perpendicular, because base and perpendicular doesn't always match that description. Adjacent means that by the letter adjacent we mean that if we have a right angle triangle, then one of the angle has to be right angle, and the other two angles are supposed to be some sort of acute angle. Now, among these two acute angles, the angle that you are now currently considering to go ahead to use for your mathematical process, that's what we are defining as the angle. This angle will be always made with hypotenuse. It will be never made with any of these two lines. One of the side will always be hypotenuse, and one of these two sides would be the other side. So have a look. This angle has two things on its two edge. One is the hypotenuse edge, and the one is this edge. If you wonder why am I talking about this angle over here, well, I'm talking about this angle over here because in applicable cases, in required cases, we might as well label this angle over here as theta. So in that case, our equations might become different. But the the two lines which make up the angle theta, one of them will always be the hypotenuse, and the other line which makes up the angle theta is called the adjacent side, adjacent of the angle theta side. And the opposite of this thing, you see, this is the opposite side of the triangle of this angle. This is called the opposite side. So that's how I prefer to do this. Now, Pythagoras' law is very simple. It gives us that h square equals to o square plus a square. So we don't have any problem over that. Now, if I try to express o and a in terms of h, so one of the things that I need you all of you to understand that this is usually happening if we define it that the vertical the square addition of squares of these two component of these two sides can give you the square of the hypotenuse, which is basically the Pythagorean rule. So you can, if you root over on both sides, you can numerically calculate out the length of the edge if you have any of these two known, and it can work vice versa as well. I mean, here you can see three variables are involved in this equation. So logically speaking, if you have access to any two of them, you can calculate out the third, no big deal. So moving on further, if we want to get a relationship among these two components, I can write that sine theta would be given by which ratio? Sine theta would be given by opposite by hypotenuse. This is the ratio for sine theta. So if I want to express opposite over here, this opposite side can be given as h sine theta. In the same manner, if I go for cos theta ratio, so cos theta is given by adjacent by height. So therefore, adjacent side can be expressed as a length of h cos theta. Now this is pretty important for you to understand that we can use this two information in a lot of cases for applicable for our benefit. How? Let me show you some example. Do you guys remember how to measure moment for your from your level syllabus? I mean, what is the definition of moment? Anyone remember this? How do you define moment?
Force into perpendicular distance from the pivot.
Beautiful. Force into perpendicular distance from the pivot. Now, one of the things that I would like to take your attention to, which you might as well come across because you are in A levels, that is the way we define work done. How do you define work done? I'm not teaching you work energy per chapter, but we will do that in the AS level. So it's not it is not a crime if I talk about this. Work done is defined as the force multiplied by the distance covered, or somebody says displacement made, equally applicable in the direction of force. You have to understand this, the force is by default a vector quantity without a doubt. Now, whenever you imply a specific direction constraint onto a distance, that basically becomes a vector. I mean, distance is not is independent of direction. Distance is a scalar quantity, which means it can be any, it doesn't have to depend on direction. Direction is not a part of its description phrase. As for so whenever you will employ some direction information with a distance, that basically becomes a displacement. For example, once again, if I tell you the definition for work done, it reads, it is the product of force and displacement made in the direction of the force, which means this is also a vector. So to tell the truth, in this case we are doing the multiplication of two vector quantities, and somehow this multiplication is resulting into work done, and work done is basically a scalar quantity. This is very much possible. On the other hand, if you try to think about the definition for moment, about a moment for a force about a pivot point is given by this expression. Moment is referred to as the product of force in and perpendicular distance of the force from the pivot point. So moment is given by force multiplied by perpendicular distance of the force from the pivot point. Now, this force, this perpendicular distance, although we use the term distance, and you should also use distance, because we cannot use that, we cannot preferably use the term displacement, because that will be somewhat confusing, because for the case of movement, we do not essentially move any object from point A to point B, so that we actually can use the term displacement, because displacement essentially means physical location change of an object. That's what we refer to as displacement. So other than referring to it as displacement, we can say the perpendicular distance and the distance of the perpendicular distance of the force from the pivot point. So সবাই এই ডেফিনিশনটা বুঝো কি? আচ্ছা, যারা এই ডেফিনিশন বুঝছো না, প্লিজ রেসপন্ড, সমস্যা নাই। I mean, I'll revise and re-explain everything that you were supposed to or that you did learn in your O levels as well. Don't worry. But if I miss out something, help me remember that. It's okay. এখানে তো সব স্ট্যাটিক ইকুইলিব্রিয়াম মোমেন্টে ডায়াগ্রাম নিয়ে আসছে। Wow. Okay, okay. No big deal. Yes, that was a keyword that was necessary. Yeah, there it is. So let's try and compare these two figures that we have over here. Have a look at these two figures. So what we're trying to show you, I mean, consider that this is a door, uh, not essentially a horizontal body, because that would be difficult for you to visualize, because you would always assume that the weight is a beneficial help that you have available. So for the time being, assume that this is a door, both of them are doors, they are hinged at this point. So this is the point where the door is hinged, so which means that if you're trying to move the door with your hand on this side, the door is going to rotate about this end. So this is the top view of our door. So try to visualize it that way, it will be easier for you to grasp. Now if we apply a force that is perpendicular to the axis of the door, so if we apply the force in this manner, in this case the application location is over here, and if we draw a straight line from the pivot point up to that point, this line pretty much produces a 90 degree with the force. Have a look. This x distance produces a 90 degree with the force, or in other words, I can say that this is the force by which we are trying to rotate the door, and this is the perpendicular distance of the force from the pivot point. That's what I mean, perpendicular distance. So there exists a 90 degree between the force and the distance measured of that force from the pivot point. So that's in this case the relevant moment would be F into x. So that's the basic definition formula. However, on this second figure, our scenario has been extended a little bit. Have a look at the second figure. What you can see here, the door was at this orientation, and we were applying the force. Yes, Ridwan, you can. So we are applying some force in this we are applying some force in a way so that the force is currently not perpendicular to the axis of the object. So what we are doing, we are applying some force that is oblique or somewhat at some angle with the door. In that case, we'll also have moment, but this moment would not be as same as this one. This moment would be somewhat different. And what would be that moment? Once again, the formula remains the same, that we have to find out the perpendicular distance from the pivot to the force, or from the force to the pivot. Now you can see that this force as a vector quantity was labeled by an arrow length of this much, because vector quantities on figure, scaled figures, they are represented as length of arrows, which means that bigger vector quantities will have longer arrows, and smaller vector quantities will have proportionally smaller arrows, so on and so forth. So length of an arrow can actually represent the magnitude of a vector quantity in any vector diagram, which we're going to see in a while as well. That's a part of our setup, part of the discussion for this chapter. So if we do force into multiplication for this scenario, one of the things that you can see, that to find out the perpendicular distance of from the force to the pivot point, we did not try to draw any line in this manner, because drawing any line in this manner, even from the very last end, would not give you perpendicular distance. Do you see any 90 degree forming up here? Have a look. If I consider this much is my distance, would this be 90 degree?
No, sir.
Anywhere. This is an obtuse acute angle. So you cannot produce a 90 degree distance only by using this much length. So this is not going to work out. So what we can do, we are going to extend the working line or action line of action of the force in a convenient direction. Convenient in the sense means that you need to, I mean, for this to find out the perpendicular distance, we could draw this dotted line on any side. We have that privilege. If you wonder that in which cases should we draw in the backward direction, I'm going to show you, don't worry. But in this case, you can see that if I extend this further back and try to join lines over here, I'm going to get more and more obtuse distances. So none of them are going to perpendicular. The only way you can draw a perpendicular on this line, if we extend the force then downwards, for this figure downwards. So we did that, and then we could find out the perpendicular distance from the pivot to this point. I mean,
Sir,
but here they, wait, here they have labeled the distance, but the actual distance, if I label the actual distance that I am trying to mean over here, that can be shown to be here. Let's say I'm gonna label this with blue. I'm talking about this distance, so that there is a perfect 90-degree between the force and the distance. So if you can find out this much distance, then you can also say that your moment can be calculated using the product of force multiplied by perpendicular distance of the force from the pivot point. Yes, bolo. Someone said, sir.
স্যার আরেকবার বলবেন উপরে কেন ডটেড লাইনটা দিতে পারবো না এই কেসটা?
ও আচ্ছা, উপরে ডট লাইন দেওয়ার জন্য কোনো মানে লজিক্যাল কোনো বাধা নাই, but if we just give, if we extend this line in the upward direction, then our aim to draw the perpendicular distance cannot be fulfilled. For example, let's say I am going to draw a perpendicular line in the upward direction. So let's say this is my perpendicular line. I might as well make this dot 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 because this is not the actual force. Now, can you draw one line from the pivot point onto any part of this extension line to make a perpendicular line?
No, sir.
That's the point. The only way you can make a perpendicular line if you extend it downwards, and this is where the perpendicular line exists. That's why extending it in upwards was not helpful for our figure. But if it is helpful for other figures, we might as well do that. The whole point is we have to measure the distance, perpendicular distance of the force from the pivot point. That's the bottom line.
আচ্ছা স্যার, থ্যাংক ইউ।
Sure. Polman, এটা কি বুঝা গেছে সবার?
Yes, sir.
So এটা হচ্ছে আমাদের এই কোশ্চেনটার একটা part, and there is another part that we have over here. That so this is one way we can actually measure the distance. Now the thing is, this can be measured in a logical manner, but there is another way we can approach a similar problem. For example, the figure that is drawn up over here, it would require some addition, I believe. হ্যাঁ, it would require a bit of addition. বলমান এখানে একটা অ্যাঙ্গেল লেভেল করা হয় নাই। This angle should be, there should be a label angle over here that should read theta between the axis of the door and the force. This angle should be labeled theta, and this force is labeled as F, which is okay. Achha, I'm going to show you this how this works. So let me show you another example. Let's say in a certain given scenario, we do not have this distance available. Rather, the question is providing us in the question this distance is available to us. So we have this distance available, which is from the pivot to the working position of the force. Working position of the force বের করা easier because let's say you are trying to pull a door. What is the most likely position you're gonna grab the door at?
End of the door.
Then you might get your fingers squashed. The most likely position to hold up a door is at its handle or at the doorknob. Do you agree?
Yes.
If you're trying to pull it down, the most likely case. Now, the reason I'm referring to this information is because if you are trying to pull the door, apply the door any force, pulling force specifically, the most likely cases we're going to apply at a fixed point, and finding out the distance of that point from the pivot point. For what I mean is that from the hinge position to the doorknob position or the door handle position, measuring that distance is actually quite simple. You just hold up a ruler and you get that distance. So in many cases, this distance would be known to us. For example, let's say I'm going to label this distance as what? Let's say P. No, not P. P was in momentum. Let's say Q. So let's say this distance is given in the question. So how can we use this information to find out the moment? So that's the part that I'm about to show you. So have a look at this figure and try to bear with me. All right, this would work. Yeah, this would work. Let's say the angle over here is theta degrees. So in this case, what I'm trying to show you that I'm trying to push the door in the forward direction. You can see that this is very much possible to make the door rotate about this hinge position, which is possible. Another version of another way to draw this exact figure can be this. I'm going to copy this up. And another logical way by which we can show this exact figure is this. Duro problem. Okay, good. So we can essentially show this whole figure in this manner as well. Now, what have I done essentially? I have moved this pushing force into a pulling force. So I move this force, keeping its alignment same. So both of these forces are apparent to be in the same line. I simply make the force appear on the top side. This is perfectly allowed in in the case of analysis of forces. If you need a force, if you want to convert a force's location, you can do that, but you cannot change its alignment. Get the idea. In this figure, I have replaced the arrow that was representing the force over here, but I have kept the alignment exactly same. Also, I have kept the length of the arrow exactly same. So these two forces, so the same force that is experienced by the door, in this case which was pushing, in this case which was pulling, would essentially mean the same thing. Or in other words, if you are pushing, let's say along this direction with some angle, this would be the exact figure for your case. But for the case of easier mathematics, if it appears to you that it would be better if I put the force over here, if you can very sensibly do that, you just have to make sure that we have not changed the alignment, which means this force and this force lines, these two lines are supposed to be parallel to each other. Kids, do I make sense?
Yes, sir.
Yes.
Okay, so this is the important bit, or one of the important bit that you really need to understand. Now, so over here, if you consider this figure over here, we have oh sorry. So now I can essentially label this as f, and if in this figure this angle was labeled as theta, why can I label angle theta in this figure? Because I would also need that angle representation to do my math. So where can I possibly label my angle in this figure? Anyone?
From the force to the axis, like downwards,
I'm sorry.
clockwise direction. From the force to the clockwise direction to the line of the door. I can't describe it.
Well, we can essentially show this force in two different ways, but I'm gonna do this in one way that would be primarily should make sense to you. Have a look. You have to understand that this angle that we have drawn over here is the angle between the force and with the object. So in this case, we also have this angle, which is an obtuse angle. Have a look with the force with the object surface. This is a rectangular surface, so a rectangular object. So both of these two faces are perfectly parallel to each other, which is essentially true. So we have an angle over here. Let's say I'm going to label this angle with green, and then we have another angle over here. Let's say I'm going to label this angle with brown. The first thing you need to understand, theta represents which angle, the green one or the brown one?
Brown one.
Which one is theta? Theta is not the green one.
Brown
The green one is the obtuse angle.
Brown
So
one.
we need to somehow label this angle. Either we could label on the lower side or we can label on the top side. Now, to make it label it on the top side. So over here, another logical thing that you can always do, you can extend your axis line. Let's say I'm gonna extend this line as per my convenience. Yes. So I have extended this line, and essentially I would like to make it into a dotted line because this was not a part of my original figure. This was my additional drawing. So I labeled this up. I hashed it up, and then I can label theta over here. What I really want you to appreciate that in terms of physics variables, force, moment, turning effect, resultant force, blah, 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 both of these figure mean the same exact information. There is no difference. Do you agree with this information? This is the part that I want you to appreciate first, that both of these two figures mean exactly same. আচ্ছা আমি বলে যাচ্ছি তারপরও কার কোনো কোশ্চেন থাকলে হাত উঠাও I'll allow you the floor, don't worry. So now we can very easily divide this force into two components. How do we do this for two components? Have a look. In this triangle formula, what we did is that the adjacent, if H is supposed to be a vector, here I only showed them as level, but if H is supposed to be a vector and O is a vector and A is also a vector, it tells us from this formula that the opposite side is the sine component of hypotenuse. I mean, this is one way to read this. H sine theta can be said, I mean, it's very simple. Because theta is an acute angle, sine theta will always be smaller than 1, right?
Yes.
Sine theta will always be smaller than 1. Now, if I write a fraction like this, for example, let's say if I write H into 3/5, how do you read this thing? In terms of H, how do you read this thing? What is this number? It is 3/5 of H, right?
Yes.
Yes, sir.
It is 3/5 of H. That's one way to read this number. So we add up a similar procedure over here, not necessarily the same. We say that the sine component of H is opposite side. So sine component means sine theta multiplied with it, because theta is taken as a default for that angle thing. So opposite side is the sine component of hypotenuse, and adjacent side is the cos component of the hypotenuse. So if I go forward, right over here, let's say this is a right angle triangle. Let's say this is a right angle triangle. So this is the hypotenuse of a right angle triangle, and try to assume a right angle triangle in this fashion over here, in this fashion over here. Try to visualize that. I'm not drawing this up because I want you to try and visualize this line. Now, because this is the force value, so I can essentially try to do one thing. I can draw the, one perpendicular, one horizontal component, which is going to work from here along this direction. Let me use green for that. So let's say I'm gonna start from this exact point, and oh, let's say this is gonna be my horizontal component, and this is gonna be my vertical component. So vertical component is supposed to be vertically down from this point. So I'm drawing this from that point, and then I'm gonna rub out the additional green part so that I have a rectangle triangle over here. Now kids, have a look. I just made a rectangle triangle over here. This is my adjacent side, this is my perpendicular side. So can I not write that this would be f cos theta and this would be f sin theta? Can I write that?
Yes.
Have a look. This is an identity, obviously. I can do that by the idea of logic. If you wonder how does that make sense, well, it does make sense. Having the force divided into two components gives us some really exclusive privileges in terms of calculation. I'm going to tell them in a bit, but before I go ahead forward, let me convince you of the fact what do I mean by these components. Components mean that if this F force did not exist on this system, if these two forces individually existed on the system. Now you might wonder, so I said that if these two forces individually worked on the system, then together they would have produced the same force over here. Or in other terms, I can tell you the vector sum of f cos theta and f sin theta will be equal to f. How? Have a look. F square equals to f sin theta whole square plus f cos theta whole square. Okay, now this is supposed to happen. That's the whole point of this thing, because this is a right angle triangle. Now if you do this, will you have f square on this side? The answer is obviously, if you're gonna get f square sin square theta over here, you're gonna get f square cos square theta over here. If I take f square common, what are you left with?
Sin square plus cos square, which is 1.
Exactly. So we're gonna have sin square theta plus cos square theta, which is ultimately 1. So ultimately you are left with f square. So the point that I'm trying to make is that if we divide these two forces into components like this very well means the force F is actually made available to us. এই লজিকটা কি ধরা গেছে সবার?
Yes,
Yes,
sir.
sir.
আচ্ছা, সো এটা হচ্ছে একটা ইম্পর্টেন্ট পার্ট। আর আরেকটা জিনিস হচ্ছে, some of you might wonder that, well, if we really want to consider this force, two forces are replacing this F force, so that their effect and their combined effect and the individual effect of the force F is identical. Okay, I'll agree to this. But in this case figure, the force F sin theta was drawn to be floating in air. How does that work? If the force is supposed to work on the body, then it is supposed to work on the object's physical location. Well, that logic is not unsound. That logic is also quite sound, and I'm going to show you another variation of this figure where we can address that issue. Okay, I'm minimizing the chat window because I need the space over here. So if any of you have to say anything, raise your hand, please. So what I'm trying to show you is that I'm going to change this figure so that I can make this force working over here, and that part would be really, really simple. Have a look what I'm about to do. I'm going to cut this vertical component off of this figure. Why did I make this? Make that. Okay, and I'm going to replace it over here, just as is. And also, I'm going to this over here. And that can also serve my purpose. Now, for those of you who are feeling skeptical yet, let me assure you of this one. What I've done over here is basically a conversion from the triangle rule into the parallelogram rule. The basic idea of triangle rule goes like this, that if you have two forces combinedly working on an object, or if you're trying to find out the resultant of two vector quantities, not necessarily forces, they can be for field strength, they can be for uh, two velocities, two velocity parts. If you're trying to find out the resultant of two vector quantities, you can go ahead and use the triangle rule. The concept of triangle rule is that you have to place those two vectors one after another, which means that the point where one of your vector quantity finishes is the same point where the second vector quantity should start. This is what you will have to achieve, and in that case, the resultant can be shown as the straight line that passes from the start of the starting vector to the end of the ending vector. So this is the idea of triangle rule of vector addition. That if you add the two vectors one after another means the second vector starts from the ending point of the first vector. Then the completing side of the triangle gives us the resultant in the direction of starting point of the first vector to the end point of the second vector. That's the idea of triangle rule. Whereas the parallelogram rules give us a bit different thing. আচ্ছা আমি এই পুরো জিনিসটাকে why not I just size it up. Okay, better. Actually, somehow আমার board size measurement নিয়ে ঝামেলা হয়ে গেছে, I don't know why. So this is the idea for triangle rule, that you place the two vector quantities one after another, and then you can find out the resultant. The other rule that we have is what we call a parallelogram rule. Parallelogram rules is the same thing, only that works a bit differently. Differently in the sense that parallelogram rule says that you are gonna have to draw a parallelogram with two of the vectors starting from the same point and adjacent sides. Let's say if I name these vectors over here, let's say I'm going to name this vector as P, this is labeled as capital Q, and let's say this is labeled as R. This would essentially mean that for this triangle to work out, vector P plus vector Q, Sadia, should be equals to vector R. Sadia,
Yes, sir.
তোমার চাল থেকে কুটুর মুটুর শব্দ আসতেছে। So এটা হচ্ছে আমাদের এই vector এই triangle ruler basic formation. On the other hand, if I convert this into a parallelogram rule, I can try this out as well. So let's say here will be my P vector, and here will be my Q vector. I am going to start these two vectors, keeping their direction and the alignment exactly same. And this is what that parallelogram rule works, that both the vectors should be started at the same point. Whereas for the triangle rule, both the vectors the vectors, not both, the vectors should start one after another. So if we complete the if we place these two component vectors, these are what we are calling components over here, because the sum of these two is going to give you the resultant. So I'm referring to P and Q as components. So component doesn't essentially have to be perpendicular. Components can be in any other direction. So yeah, so I'm drawing the components over here as starting from the same point, And if I now complete the parallelogram, considering these two sides as the two sides of a parallelogram, I can very well get a parallelogram that looks like this. Now I have to draw the diagonal from that same starting point. And this diagonal would also give me that exact resultant. So I can label R over here as well. Now you do understand that this is basically, I mean, this rule and this rule are not very much different, because if I consider this whole structure as a parallelogram, then this side and the length of this side and length of this side, I mean, should also be same. So like I said a bit earlier, that we can essentially replace a vector from one position to another position. কোথায় যেন এটা দেখালাম? এখানে. So we can essentially replace a vector from one position to another position without changing its magnitude and its direction. Direction in this case means alignment. We can replace it anywhere. So that's basically what we did over here, is that we simply took this vector from here and brought it up at this position and make this into a right angle triangle. So that's essentially what we did. So what essentially this means, because this is so not right angle triangle, made it into a triangle, normal regular triangle. So in this case, so this was the side in the triangle rule. We just brought it up over on this side to make it into a parallelogram rule. So this means that this side is also equal. So if we just forget about this part, let's say if I just rub off this part, you should be able to see triangle rule as well. Let me just show this to you. So let's say I'm gonna block the lower part. Do you not see the triangle rule even yet? For the upper part, you should be able to see the triangle rule. So basically both of the rules pretty much mean the same thing. We just have two different names, because whoever devised this had to decide that I'm gonna make the kids suffer and come up with two different rules. So why not? So we have that. So we can have, so the reason I'm discussing this with you, and in this case also, the sum of these two components, P plus Q, will give you the resultant, and that works perfectly as well. So the reason I put this up is I'm trying to show you over here that whenever I am replacing this floating f sin theta, I'm using the term floating because apparently this f sin theta is not working on this door anymore. It's working on the empty space. So that's why it's the term floating. So to avoid this floating problem, I replace the f sin theta to the left side, starting or working on the same exact point. Now, if I want, if I divide this whole thing, if I divide this whole, so if I consider this thing to be as a as a parallelogram, well, this is not essentially a parallelogram, this is a rectangle, but you should know from your geometry knowledge that every rectangle is also a parallelogram. Do you know that?
Yes, sir.
Why is that?
Because all the
Because
sides
opposite sides are equal.
yeah,
Opposite sides, sir?
equal and parallel.
Equal and parallel, exactly. That's
And
essentially the minimalistic and required definition for a parallelogram, that it is a quadrilateral where the opposite sides are supposed to be quadrilateral ball like that. You can also have a hexagon which has its opposite sides equal and parallel, but that's not a parallelogram, that's a hexagon. I don't know what's the name of that kind of hexagons, but you need to first mention a quadrilateral. So a quadrilateral which has its opposite sides equal and parallel is a parallelogram. So a rectangle is also that. Only the difference is that a quadrilateral which has its opposite sides equal and parallel, and also the each of the inside angle, or you can say one of the inside angle, because that basically takes care of the whole thing, is 90 degree, or is a right angle, is a rectangle. So that's why if I now consider these two sides, the green side and the ash color sign as the two part of my parallelogram, I can go ahead and try to complete my parallelogram, let's say with a blue line. So this is my horizontal completion, this is my vertical completion. So I have a parallelogram rule over here. So in this case, I can very well write that, well, if this is the parallelogram rule, then logic tells us that f should be equals to f sin theta plus f cos theta. Do I make sense?
Yes, sir.
ঠিক আছে, বলবেন একটা জিনিস খুব ভালো করে খেয়াল করো, এটা খুব ইম্পর্টেন্ট। Whenever I'm writing them as vectors, I'm using the sun vector, I can actually write this equation that f equals to f sin theta plus f cos theta, which means if you do add them in vector geometry, you're gonna come up with this. But you cannot write this equation without this bar signs. That would be highly wrong. Because if you write this equation, f equals to f sin theta plus f cos theta, and you feel like that f sin theta পড়াইছে, এটা তো জীবনে ভুল হবে না। No, you're wrong. In this case, well, you should not ever think like that. I was not trying to have some vanity there, but I was trying to I mean to warn you that I can be wrong. I'm wrong in a lot of cases still, especially যখন এটু দেখে পড়াই তখন অনেক জায়গায় দেখা যায় গড়বড় হয়। So ওগুলো আবার পরে ঠিক করি। I have always have I'm lucky to have really intriguing students who actually can sort out those mistakes, who actually understand the discontinuation in the lecture, so that they ask me questions, we can figure it out. I am prone to mistakes, so I can do mistakes. So don't take my word for granted unless I ask you to do that in specific cases where I don't want to draw the additional discussion, which is not a part of your syllabus. Anyway,
স্যার
yes.
স্যার আমার না ওই যে ট্রায়াঙ্গেল রুলটা বুঝতে একটু সমস্যা হচ্ছে। ট্রায়াঙ্গেল না মানে ওই যে এই যে এই যে এই যে এটা কি বলে কাইটটা
Parallelogram rule. Parallelogram rule.
হ্যাঁ
Parallelogram rule.
প্যারালেলোগ্রাম রুল। ও
Yes.
আচ্ছা আচ্ছা মনে পড়ছে।
Okay. So the point I was trying to make is that you can never write an equation like this. This is highly wrong, because this would essentially mean that numerical value of f sin theta plus f cos theta would be equals to f. But that's not the case. That will never be the case. The vector sum of these two components would be equal to this vector quantity. But if you want to go for their values, you have to take help for the Pythagoras. So you have to give in some squares. Now you are good. Do I make sense?
Yes, sir.
বুঝা গেছে? ভেক্টর সাইন
Yes,
দিয়ে
sir.
তুমি ডিরেক্ট লিখতে পারবা, বাট যদি তুমি শুধু ভ্যালু দিয়ে লিখতে যাও তখন তোমাকে পিথাগোরাসের ফর্মুলা ইউজ করে স্কয়ার দিয়ে লিখতে হবে। So this is the basic idea that I wanted to show you over here, and there is more part to this thing. That is, why did I came over here? I came over here to give you an idea that how could you possibly measure the moment for this case. What are the two different ways I can measure the moment for this scenario? So there are two different ways I can do this thing. One of the way is that, where is my original figure? There is my original figure. So let me take that out once again. Should I? No, not. So one of the ways I can try and draw I can try to measure the perpendicular distance for this scenario is that I can try to attempt to draw a perpendicular line from this point onto the force line anyway. So I can try to draw it anywhere, and you can see that somewhere over here I can pretty much draw an approximately normal line, which I believe is normal. So just to make sure, I'm going to give an arrow over here. Now in this case, for this drawing, the force line was long enough that we did not have to extend it backwards. But if it is needed, we might have as well have done that. So have a look. This is a part that I want you to appreciate. If this is f and this the length of the distance along the door side is labeled as d, and let's say this much distance is x, I can pretty well write that just a second. I'm sorry. So I'm labeling this distance along the door side is d, and I'm labeling this perpendicular distance as x. Now what I need you to understand, by definition, the moment that should be happening in this case should be m equals to fx. Now, if I try to get the value of x in terms of d and theta, how can I represent x? X can be replaced in terms of d and theta by how? Have a look. This is a right angle triangle, but this is your theta. So this is your d. D means this is your hypotenuse for this right angle triangle. Would you define x as the adjacent side, or is it the opposite side of angle?
Opposite.
Everyone, have a look. How would you describe this side of this right angle triangle? It is opposite side, yes, if you are correct. So here is a hypotenuse, here is one side, here is another side. So x is which side? Is it the opposite side or is it the adjacent side? বললাম বুঝতেছো কি বলতেছি? না বুঝলে রেসপন্ড করো, I'll help you to understand. So this would be the opposite side. So I can pretty well write this as the moment should be equals to f into d sine theta. So this pretty much serves our purpose to calculate the moment using this three information: the force, the distance along the door where the force was added, or in other case, like I said earlier, that the distance from your hinge to the center of your doorknob or door handle, and the angle at which you are applying the force. So you can do this. Alternately, we can pull this force up over there and we can try to calculate that. For example, let's say if I take this figure and copy paste it over at the bottom, some reference. So let's say I now have the force located over there. Now comes the idea of our extension line, that in this case, I cannot draw a perpendicular. So let's say I don't have these components over here. I'm going to rub off the components because the component parts I'm willing to show it a bit later. So let's say rub off these things. Let's say this is the case right now. So I just replaced the bottom force on the position of the top of the door, which is perfectly all right. Now, if I want to label the distance x, which is the perpendicular distance from the pivot to the force, can I do this while attempting drawing a line from this point onto the force line? Can I get a perpendicular line over here? Have a look. For this part, can I make a perpendicular line? For any of the position, do I have a perpendicular position? The
No,
answer
sir.
is a no.
Sir.
If I go even further in the forward direction, that would be even more impossible. But somewhere down, it is possible. So that's essentially why I'm gonna first try to extend this line in the same alignment. Let's say this is the alignment of the force. I can draw this line as big as I want, no big deal, because you're just extending the working line of the force. You might as well make it into dotted lines because this is an additional drawing. And then you can draw the perpendicular. Let's say I'm going to draw this with deep blue. Yes. That might as well look like this. So that's what I meant. So this is the force working along away from the object, working at this position. So, and also this is your x, this was your d, and the angle that was produced over here was theta. Now, in real cases, in many cases, this angle theta would not be given in the factor. Let me just rub this off. In your figure, if the force is shown over here, in your question, you would have the available information that the theta was produced over here. So that might be that is the most common case. Now you can see very well, if this angle is theta, the opposite angle should also be what? Theta, because these two lines are straight lines. They're cutting each other at this point. So opposite angles are supposed to be equal. So in this case scenario as well, we can also write from this right angle triangle that x equals to d sine theta, which ultimately leaves us to the equation that moment equals to fx, force into perpendicular distance of the force from the pivot point, which also means F into D sine theta. So we pretty much end up with the exact same equation we got a bit earlier, F D sine theta. Here also we got F D sine theta because it's not going to be a variable. So these are the two different ways I showed you in terms of the position of the force. The third way, which is actually the most convenient way for mathematical operation, is to go for this division. Now, if you wonder why does this division work or why is it important for us, let me tell you this idea in a simple way. Assume that a door hinges are infinitely strong, which means you cannot break it off, or you cannot push it enough with your own physical forces to break the wall to which the door and the choke cutter English key. Anyone know the name of English name for choke cut? I mean the frame in which the door sits. কেউ জানো?
It might just be called door frame. I don't know.
Acha, okay, door frame works. So let's say you have a door that where the hinge joint is infinitely strong. Now I'm taking infinitely strong just to give you one idea that if you let's say open the door and veer the door at some angle, and now you try to push some force exactly along the, I mean, if you try to push the door towards the hinge exactly, or if you try to pull the door out of the hinge directly, you shouldn't be able to make any movement or any rotation of that door. You cannot, because if you're pushing exactly aiming, I mean, let's say you are pushing the door on this surface. I'm talking about this surface, and you are strongly pushing towards the pivot. You cannot make any force. You cannot make any movement. The door is not going to rotate. The reason is very simple. That simple reason is what I'm about to show you over here for the idea of component division. So let me just take this figure. Paste it. So have a look. If you what is happening over here is that we have two forces. F is working over here, F sine theta is over here, F cos theta is over here. If F cos theta in this case is actually the pulling force in this direction. Now, what is the perpendicular distance of F cos theta and this force? That would be 0. Now you might wonder, sir, এখানে তো একটু perpendicular distance আছে. Well, এখানে একটু perpendicular distance আছে, but we should consider this to be negligible. Or another better way should have been that I should have been careful about this drawing in the first place, and I should have had drawn this figure in this fashion. That would have been a better choice, so that the force was shown from the starting from the axis of the object. I mean from here. That would have been a better choice, but I didn't do that. So consider for the time being that this distance over here is negligible, or it is not working, it is not available. So what I'm trying to mean over here is that this force F sine theta is working perpendicular to the line. So let's say this is the distance d, and this force F cos theta is working along the axis of the object, which is not going to produce any moment whatsoever, because this F cos theta has 0 perpendicular distance with the pivot. So if you think about the equation, the moment for this horizontal component F cos theta can be written as F cos theta, which is the force, well and good, multiplied by 0, because from the pivot point to the F cos theta force, the length is 0, perpendicular distance is 0. So ultimately this will not give you any moment whatsoever. This F cos theta component of the F force is not going to give you any moment whatsoever. Can we all agree on this fact? Check this out. Because the force is directly working along the line of pivot, this force will not give you any key, any moment. Does that make sense?
Yes, sir.
আজকে নাই কে কে জারিফ কই হ্যাঁ আচ্ছা anyway everyone if you have any question please respond if you're not responding I'm assuming that you don't have any question yet so that might come from either you're not listening which is a very common cause or it might as well be that you are listening but you actually understood that's why you don't have any question which is the expected outcome so have a keep looking and if you have any question please ask me about it. So the point I'm trying to make that f cos theta force would be there, but the perpendicular distance of the f cos theta force with the pivot point would be 0. So if you do the multiplication over here, the total moment produced by this one would be also 0, which essentially brings us to the remaining component f sin theta. So we have divided f into two parts, f cos theta and f sin theta. So it is, I mean, having these two component forces working individually on this component on this door is the same, has the exact same effect as this force F individually working on the door. So that was the whole point of dividing them into components. So with the reason we divided it is because we have the advantage that we can now altogether get rid of the component of F cos theta. We don't have to even bother about that because this one's alignment was along the pivot line, which means all the moment that this F force could possibly produce is going to be produced from this F sin theta or the force component that is perpendicular to the distance d already. So now we have a perfect 90 degree over here. So I can write from this figure automatically that the moment that we'll be getting should be how much? F sin theta into d. See if it makes sense. This one should be F sin theta. My God. This is just a moment. Do you know what is one of the most common uses of aluminum silicate? Anyone?
Yes, sir.
Aluminum silicate is the most common ingredient for talcum powder. It can convert it into extremely fine powder, which are extremely dry, because silicates are very hydrophilic, dry, and if you have enough on a surface, they're gonna make that surface dry as well, because they're gonna absorb that thing within their silicate crystal structure.
So it's also used in antiperspirants.
বুঝি নাই
Antiperspirant কি use করে aluminum silicate.
বুঝি না আবার বলো
Antiperspirant spray তেও কি use করে aluminum silicate.
antiperspirant spray, I'm not exactly sure, but they might. Aluminum silicate is extremely insoluble in water, or but if they use a different type of solvent, they might as well use it. Well,
So antiperspirant এর জন্য যদি use করার কথা, so it would stop your perspiration thing.
আচ্ছা, পার্সপিরেশন স্টপ করার আবার আলাদা আলাদা মেকানিজম আছে। একটা হচ্ছে যে certain antiperspirant spray works in the way that they actually keeps you dry, and that's why the bacteria cannot work and you don't smell bad, which is basically how the talcum powder works, which works for a while. And there are certain other antiperspirant spray, for example, the most common case are the roll-ons, that they somehow actually clog up the
Sweat
sweat pores for a duration. So if you're using roll-on devices, it's imperative that you take a shower every day so that you eventually open up those pores so that those sweat things can come out. Because if you keep using roll-on devices and don't shower for days, you might actually start having pimples and stuffs and clogs up in your skins. So I'm not essentially sure about how antiperspirant works, but aluminum silicate is a key component for talcum powder that I know for a fact. So that's why I wanted to share that. Acha. So the moment produced by this F sin theta force would be F sin theta into D. So that can be also written as an altogether FD sin theta. You can see that for all of these three different cases that we try to calculate the moment, we pretty much end up with the same expression: FD sin theta, FD sin theta, FD sin theta. So that's the point that I wanted to get in your head, that as for how can we calculate the moment. Any questions so far? এই তিনটা স্টেপ বুঝা গেছে সবার ডিটেইলসে?
জি স্যার।
Anyone else? We have 23 people over here. Give me some notion, like either respond in the voice chat or write in the chat window. যে বুঝা গেছে, yes or no?
Yes, sir, got it.
স্যার বোঝা গেছে।
Okay. Thank you. Thanks for your response. So that's so in this figure also I also pretty much covered the basic idea of triangle rule and the parallelogram rule, which is somewhat a bit old concept from your O-level syllabus. So we can move ahead forward. In the note, I actually came from here, and on the very next thing we have the vector geometry. Vector geometry is R equals to P plus Q. Triangle rule means components are placed one after another. Parallelogram rule means components are placed from the same point. So we have two vectors, let's say P and Q, which we want to find out the resultant for. You place one after another, you get the R. So and the parallelogram rule, the student did not prefer to write the whole sentence, whole word, which is a really smart move. Only use symbols works for me. Parallelogram rule: you start the components from the same point, complete the parallelogram. The diagonal starting from the same point gives you the resultant. So this is the basic idea over here. This next figure is a pretty interesting figure. I want all of you to understand this figure really, really carefully. One, the triangle rule and parallelogram rule only handles with vector addition. So you can only do the sum of two vector quantities using triangle or parallelogram rule. So what if you ever have to do some subtraction of vector quantities? Then what? Well, if you know how to add two numbers, you also know how to subtract two numbers as well. Subtraction is basically an addition where one of the number is negative. I'll tell you again. Subtraction is basically an addition where one of the number is negative. That's one way I can change the description of an addition of a subtraction process. Does it make sense?
Yes,
Subtraction is just another addition process where one of the number is negative. So that's what we're doing over here. Let's say R was defined as the sum of P plus Q over here. So we found out R over here. Let's say another vector quantity Z that can be found as the subtraction of P and Q. And we're going to show this in a vector diagram. So P minus Q can be written as P plus minus Q. Now, the reason we have written this expression over here in this form, because we are trying to mean it very precisely, that if we do the vector sum of P and minus Q, we might as well get Z. Now, what would be minus Q? Q is working in this direction, having this much length of arrow. Minus Q would have that exact length of arrow, that exact alignment of working, but direction will be exactly opposite. Which means if Q is over here, Q is along in this direction, let's say by 2.5 centimeter, minus Q will be in this exact alignment in the opposite direction. So just the other way around of the exact same length. So that is what is shown over here. So P is same. At the end point of the P, we are drawing minus Q. So Q was going this way, minus Q is going this way. Do you see? So now these are the two vectors which are placed one after another. So P and minus Q. So if you do the vector sum of these two things, which means that if you start your resultant from the starting point of the first vector and end your resultant at the end point of the second vector, you get your resultant. So Z equals to হচ্ছে Z is the resultant of P and minus Q. This triangle has the exact same meaning as this triangle. I don't want to describe first, but I want everyone to have a look and see what is changed over here.
Sir, isn't it supposed to be Z plus Q equals to P?
Yes, it's supposed to be that. The student was wrong in writing that. My bad. বলো মানে এই কোশ্চেনটাতে ভুল আছে। How can I not?
স্যার এই কোশ্চেনে তো P plus Q equals to R হবে তাই না?
Yeah, P plus Q equals to R হবে। P plus Q equals to R হবে, which is for the triangle rule and for the parallelogram rule. But do you understand that why these two figures are equal? Could you find out the difference? What changed in these two figures?
Sir, Z is the negative. Oh no, sorry. The direction of Q is different in
On the right
in the
figure.
both figures.
Yeah, direction of the Q is reversed on the right figure, and because we reverse the direction, we also take away the minus sign. So minus Q shows in this way, Q shows in that way. So what I'm trying to show you in this figure, by using these two figures, that in appropriate cases, you can essentially change the notation of a vector quantity by plus or minus only by reversing its direction. And it's perfectly allowed, and you can do that for your convenience, for problem solving, especially in the MCQ questions. This can be a very useful trick, that you can convert a vector diagram by changing one of the component or any of the component reversely. So what is done over here? This is this one. Now if you have a look at this figure, what you can see, that these are the two vectors which are now placed one after another. Do you see that?
Yeah.
These are the two vectors which are now placed one after another. And this is the vector which is starting from the first point of the Z, ending at the end point of the Q. So I might as well say this figure essentially means Z plus Q equals to P, which is basically obtainable from this equation. This was wrongly copied from the board. I beg your pardon. So
It's okay, sir.
If you just replace this force over here, you can pretty much get that part as well. So that's how we do vector subtraction. We do not essentially go for a different set of rule for subtraction. We just reverse the vector which we are supposed to subtract and go ahead and do our drawing. No big deal. এই পার্টটা কি বুঝা গেছে সবার properly?
Yes, sir.
Yes, sir.
এখানে আমরা কাপল জিনিসটা বুঝাইছিলাম বলে আমাদেরকে। কাপলটা বোঝানোর আগে এই পার্টটুকু ইম্পর্টেন্ট। এই পার্টটুকু অ্যাকচুয়ালি স্টুডেন্টরা কপি করে না, বিকজ most of this part was actually drawn from your O-levels logic, except for this figure maybe. That component division was not introduced in your O-level. Component division is actually introduced in your AS level. And this is the easier way for you to do mathematical operation, because you don't essentially have to do much drawing for this figure. I mean, এখানে আমি তোমাদেরকে f cos theta, f sin theta একে দেখাইছি, but if you are only given this much figure, I mean, let's say if you are only given, I don't want to draw this again. Let's say you are only given this much figure where these components are not drawn for you. You're only given this much figure. And from this figure also, you can very easily calculate out the moment of this figure. Let's say in this case, the D is also provided to you. So you can very well say that the moment produced by this F force would be FD sin theta. Do I make sense? বুঝা যাচ্ছে কিনা?
Yes, sir.
So এটুকু হচ্ছে নতুন জিনিস, and then the new topic that we have is the new concept that we have is what we call a couple. Couple এর definitionটা খুব ভালো করে খেয়াল করো. There are 3 exclusive points in this definition.
Equal, parallel, and opposite.
Two equal, parallel, opposite forces are called a couple. Well, এখানে একটা পয়েন্ট হালকা বাদ পড়ে গেছে, সেটা হচ্ছে these two forces should not work in the same alignment. If two forces work in the same alignment, they will not produce any turning effect. What I mean is that try to visualize or imagine an object that is located in space. So let's say this is a bar. This is a bar that is located in space. Located in space means that try to imagine that this is just moving around. If you apply two equal forces at the same position in opposite direction, let's say I'm going to apply two equal forces over here. So one along this line and the other along this line. And let's say these two forces are exactly equal to each other. They will not give you any turning effect. To have a turning effect, I mean, have a look. These two forces are equal in magnitude. They are opposite in direction. They are parallel to each other because they are both vertical, but they will not produce any moment. To have any moment, there has to be some gap between the two forces. That way you can produce a moment. Now think about this. In this case, if there are two forces working in this manner, this bar is not going to move, neither is going to rotate. But only if I may move this force, this one, a bit on one side. Let's say I'm going to cut this off from here and move it a little bit to the left. If I apply it something like here, then these two forces are going to start to make this rod rotate. What will be the rotational direction of this bar? Can anybody guess?
Upward.
Rotational direction. Rotational directions are clockwise or anti-clockwise.
Anti-clockwise.
Anti-clockwise. Anti-clockwise.
Beautiful. By default, this object is going to try to rotate in an anti-clockwise rotation because the forces are doing that. This part is trying to go up, this part is trying to go down, so it's going to rotate in anti-clockwise direction. So yeah, that's the point that I'm trying to make, that this kind of or arrangement of forces is what we call a couple. Now, there are there is a new word that we're going to learn, which is called torque. You might as well know this thing, but torque is a synonymous word for moment. Torque and moment can be used replaceably. So you can replace the word moment at any place where you are supposed to use the word torque, and vice versa. The only key
Sir, for a couple moment or torque to occur, the pivot must be in the middle, right?
I'll talk about that in a bit. I have to go up to the point of the figure. I'm still defining the definition. So the torque and the moment, they are both synonymous word. They can be used replaceably. So I'm not sure if replaceably is a word, but just bear with me. So, but for most common usage, the way the grammar works or the sentence making, I mean the language works, is that typically we use the term torque for a couple, and typically we use the term moment for a single force. But if you ever write torque of a force, or if you write moment of a couple, you are not going to be mistaken. They would be equally correct. In terms of physics, they'll be equally correct. But the way our language works is that torque of a couple is a more common phrase. Moment of a force, single force, that is a more common phrase. Torque is represented by tau. The tau symbol is looks like this. I might as well show you this in the written version. This is how tau looks like, sort of a fashioned top and a carved bottom.
Stylish T.
Yeah, sort of. So yeah, T is like this. This is tau. This was like, I mean, many of the alphabet that we have were adapted from Greek, and tau was the Greek symbol for T. Then the English linguists defined, we are not going to work with so many curves and everything. We're simply going to make it look like this, which works. No big deal. So yeah, tau is represented by this symbol. This is a figure that can apparently look to be quite a whole turmoil, and we have a lot of different boxes over here for different calculation. So this kid actually over here wrote everything very neatly for all the different points over here, and we're gonna definitely discuss this part, but not today. আজকে তোমাদের এরপরে ক্লাস কবে?
Saturday.
এরপর ক্লাসে স্যাটারডেতে?
জি স্যার।
Yes, sir.
আচ্ছা ঠিক
It's
আছে।
on Saturday, sir.
So we'll start discussing from this figure on our Saturday class from onward, and you should cut off this line, or at least remember that this line was quoted wrong. This is supposed to be z plus q equals to p, which is perfectly all right. We are all prone to mistakes. I am also, so disregard that. And then
Sir?
I'll continue further to the line. Yes, bolo.
স্যার একটা কনফিউশন ছিল, আপনি এখন এই যে দুইটা ফোর্স দেখালেন না, একসাথে ওয়ার্ক করছে কাপল
Yes.
ওই যে ছবিতে। হ্যাঁ স্যার, এগুলো যখন মানে একই লাইনে ছিল, আপনি যে বলতেছিলেন যে কোনো মানে এটা নড়বে না,
Yes.
তখন আপনি বললেন না যেটা প্যারালাল হবে, এটা প্যারালাল মানে হওয়ার জন্য ডাইরেকশন সেম হওয়ার দরকার ছিল না?
No, 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 no. Let's say if I draw a straight line, and if I draw two different lines onto this same straight line, let's say one is green. My bad. I mean, বলতেছি parallel. I mean, vectors which have the same alignment can be said to be parallel to each other. What I mean is that if you have a vector that is working in this direction vertically upwards, and the vector also working over here vertically upwards, we can say these two vectors to be parallel. And the vector that is working vertically downwards, all three of them are said to be parallel. But if there is a bit of an angle in someone else, let's say this red vector is working with a bit of an angle, then we cannot say these vectors are parallel. So whenever these two forces were perfectly in the same alignment, this was working vertically upwards, so it's a vertical line, and this was working vertically downwards, so their alignments were parallel. Parallel means their alignment, not location. বুঝতে পারছি?
জি স্যার।
Okay, beautiful.
থ্যাংক ইউ।
No problem. So we'll pick up from this point from next class. তোমাদের আজকে ক্লাসে কোনো হোমওয়ার্ক নাই, যারা কাইনেমেটিক্স বা হচ্ছে মেজারমেন্টের ওয়ার্কশিট বাকি আছে এগুলো আস্তে আস্তে করতে থাকো, get busy with it, and thank you very much for today.
আসসালামু আলাইকুম স্যার।
Thank you, sir.
Thank you.
Assalamu alaikum, sir.